Welcome back. So what I'd like to do in this video is preparing for Precalculus is go over some basic functions as well as the transformations, how we can transform that graph and how that is going to affect their domain and range. So in this video, what I'm going to do is just kind of discuss 8 basic functions, ones that should be familiar with you from, Algebra 2 or Algebra 1. And then what we're going to do is look at their domain and range and then apply some basic kind of transformations to them and then see how the domain and range is affected or changed. Now, I am going to use graphing technology. In the pre-calculus curriculum, these problems is kind of expected that you are familiar with them, so you don't always have to rely on graphing technology, but that's kind of for the course we're going to use graphing technology in this, and in this video, I'm just going to go ahead and plot the graphs on Desmos. So let's go ahead and get started with the first one is y equals x. Now, in y equals x, that is the identity function. So hopefully you kind of already know that that is a line, something we've talked about many, many times. But let's just go and take a look at this function and just make sure we kind of know what it looks like. So y equals x already highlighted over here. And you can see here that this graph is just kind of has like this nice perfect line. Now, when identifying the domain and range, that's kind of like the first portion that we're going to be looking here. We're basically, by looking at the graph, we're basically asking ourselves for the domain, how far does this left continue going on? And if you keep on zooming out of this graph, you're going to see that the graph is just going to continue indefinitely, keep on going to the left as well as going to the right. So when identifying the domain for this function, we can say that the graph is going to continue going to the left all the way to infinity and is going to continue going to the right all the way to infinity. Now, the range is basically asking us of the graph, like how low is this graph going and how high is this going? And again, as we zoom out, we see that this graph is really, there's no restrictions on it. There's no reason that we would believe that the graph is going to stop going down or stop going up. So therefore, we can say that the graph is going down to negative infinity and going to continue up towards infinity. So let's just go ahead and sketch a quick rough little sketch of the graph just so we have, ooh, that's really bad. Okay, so let's, just a nice little sketch just so we can, that goes through there, just so we can remember what the graph looks like. So for the domain, I'm going to say from negative infinity to infinity. And for the range, it's going to go from negative infinity to infinity. Now, a couple things that is I'm using parentheses, and we'll talk about the use of parentheses, but basically parentheses means that the value that we're discovering for or using for our domain is not defined. And since infinity is not a number, we're just knowing that the graph is continuing down indefinitely. So infinity is not a number, so therefore it is not actually contained within the domain. However, when we look at this next example, which is the quadratic function, okay, so we move over to the next one, you see the quadratic, and that is kind of like our U-shaped graph, right? Now this one is the same as we kind of expand out. We can see that this graph is going to continue to keep on getting like wider and wider, right? It's not getting as wide as it used to, but it's still getting wider and wider. However, when we look at the range, we see that the graph only goes as down to 0. And even though we can keep on zooming out, there's really no reason for us to see that the graph is going to be turning and then shooting down lower than 0. So we can say that the domain, again, is going to be from negative infinity to infinity because it's going to keep on getting wider and wider from left to right. But the range now is going to be limited to only going down to 0 and then going up towards infinity. So we're going to have to write our domain and range a little bit different here. Well, not really the domain. The domain is going to be the same. That's negative infinity to infinity. So that's just kind of our U-shaped graph. Let me try that again. Something like that. Really bad with this tablet. Try. So the domain is going to be from negative infinity to infinity. And now the range is only going down to 0. Now 0 is a real number and 0 is defined. So rather than using parentheses, I'm going to use a bracket. So it's going to go from 0 to infinity. Now again, infinity is not defined, so we're going to use that closed bracket. The next one is the absolute value function. Remember, the absolute value is, basically saying like the absolute value distance, away from 0, or at least is like a definition. But as we look at that from a graphical perspective, what we'll notice is this looks like the v-graph, and it actually is very similar to the identity function, positive and negative. Like if we were going to do negative x, then that line would continue that way, right? So you can see that, again, this graph keeps on continually expanding to the left and to the right, but it also is restricted, not going below 0. So the domain and range for the absolute value function is going to be that exactly of the same as the quadratic function. So we can actually just go ahead and rewrite that exactly the same here. Let's just do a nice, try to sketch a nice little V-shaped graph. And again, I'm not trying to be perfect, but I just want to kind of have like a basic idea of what the graph looks like for you, just to write it down so we have an idea. Negative infinity to infinity. And then the range, again, that 0 is a defined value in the range. So that's going to be from 0 to infinity. Okay? So these we discussed, in Algebra 1, Algebra 2, so they should be somewhat, familiar with you. And then we start getting into, some other ones as far as like the square root of x, y equals 1 over x, and then as well as y equals x. So let's go and take a look at these. So y equals square root of x. That is going to be taking like the square roots, if you remember a number, like square root of 4, square root of 16, square root of 9, and so on and so forth. And if we used a table, we could go and look at the graph, but we can kind of hijack this a little bit. Let me zoom in here. And you know that in the real number system, we can only take the square root of real numbers. It's not letting me get to 1. Maybe I'll try 4. Oh, it's being very fidgety with me. There you go. Square root of 4 is 2, right? That's a point on the graph. And obviously we could get to 9 is there. Square root of 9 is 3. It's been a little touchy. But we can see here now the domain is limited, right? We can see that the domain is limited to only positive values, right? Because you can only take the square root of positive numbers. And therefore, if you can only take the square root of positive numbers, you're only going to get back positive numbers. Taking the square root of a number is not going to equate to us getting a negative number. So so therefore we could say the domain is restricted for all positive values. And again, 0 was a defined value. So the square root function just looks something like this. And a lot of times too, we'll use that a dot to kind of represent that, but we'll talk about that in a second. So the domain here is going to be from, oops, I'm sorry, that's a bracket because 0 is defined. So that's from 0 to infinity. And then my range is going to be, did I forget? Oh, I forgot one. And then my range is going to be from 0 to infinity. And sorry, I had this all zoomed in, and I forgot to go over x cubed. So let's go and take a look at x cubed here real quick. So y equals x cubed, if we go ahead and take a look at that graph. I was wondering what I did with my logarithms. If I go and take a look at my x cubed, you can see that this graph is kind of like what we call the S-curve graph. It's not really restricted in any ways. If I keep on like zooming out, you can see that this graph is going to continue expanding left and right, so therefore the domain is unrestricted. And you can see it's also going to be expanding up and down, so therefore the range is going to be unrestricted as well. So therefore the domain and range of that function of x cubed is going to be all real numbers for both. So let's go ahead and just sketch a quick sketch of that. So a nice little S-curve that definitely goes through the origin. And we'll write our domain is from negative infinity to infinity. And our range is from negative infinity to infinity. One thing I forgot to mention is I'm using what we call interval notation to write the domain and range. We will discuss other ways to write the domain and range. In the class using like set notation and inequalities and, a lot of times just maybe even writing them out, so on and so forth. So we will look at different notation, but for this, I'm going to just be focused on set notation. I'm sorry, interval notation. All right, so in the last example, we could see that, now that was the first one that our domain was restricted. So previously, our range had been restricted, particularly for the absolute, or for the quadratic as well for the absolute value, our range was restricted. When we got to the square root, you can see that my domain and my range was restricted, right? Because you can only take the square root of positive numbers. Let's go and take a look at 1 over x, because that's something that's very important here. So when I go ahead and sketch 1 over x, we said, look at that graph. That's kind of nice. It looks like it's getting really, really close to 0 on all these elements. And, I could go ahead and zoom in here. And it looks like it keeps on getting closer and closer to 0, but it doesn't look like it actually ever reaches 0. So that's what we call approaching 0. And the same thing happens no matter what axes, wherever you're going, because it's actually never going to equal 0. It's actually approaching them, and that actually comes into asymptotes, which we'll talk much more in depth as far as in the course. But the important thing for you to understand here is you could play around with this graph and get really, really close to 0 on the x-axis, y-axis, but notice that the graph is always going to be approaching and never actually reach 0. So those are asymptotes, so those are undefined values. So we see for the domain, which is the set of values left and right, we see that the values are true, right? There's x values everywhere except for when x equals 0. And then as you go to the positive values, we have values that are, defined for our domain. Our range is defined, looks like, for all values. Looks like this just continues going down, right? It's defined for all y values, negative as well as positive, except for when y equals 0. So it looks like the domain and range is defined for all values except when x equals 0 for the domain and when y equals 0 for the range. So there's a couple different ways we can write that. Let's sketch the graph here real quick. So the graph is called a hyperbola. And just going to do a rough sketch, just so I can kind of remember what the graph looks like, because I hate drawing on this little tablet thing anyways. All right, so the domain is kind of broken up into two sections. We had the y values when there was for negative, and you could say, well, that was going from negative infinity. That's a parenthesis. Negative infinity to 0. And then the positive version, now 0, again, I'm using the parenthesis because 0 is undefined, right? And if we go back and look at this graph, let me just continue. And then 0 is not defined, and then we kind of jumped from 0 to positive infinity. So there's kind of like, we write the domain in like two different intervals here. And again, let's just look at the graph. From negative infinity to 0, the graph is defined. From 0 to positive infinity, the graph is defined. The only time it's not defined is at 0, but it's okay. We covered that because we're using parentheses here, not our brackets. Now, I do need to group these together, so I'm going to use the nice little union symbol just to say that these are a part of the same domain. Now, the range is actually the exact same. When I do the range, we looked at that, and it was the exact same just for the y values. So that's going to be from negative infinity to 0, and then union 0 to infinity. All right, let's go ahead and look at y equals e to the x now that we've kind of talked about some asymptotes here. So when I go ahead and take a look at y equals e to the x, we can see that this graph looks like it's going, again, looking at it's going to 0, but what we notice is, and even if we kind of zoom in here, it's not actually going to actually equal 0. It looks like, again, it's one of those approaching but never actually equaling values. And I don't want to spend too much time zooming in, but you guys can see that, yeah, it's getting really, really close to it, but it's never actually going to reach it. So again, we have another horizontal asymptote at y equals 0. So the domain is unrestricted. It looks like this graph continues going to the left. It looks like it's going to continue going left, continually approaching 0, but it's not going to stop. And as it goes to the right, it's going to just, looks like it's going to keep on increasing, but continually going to the right. So the domain is unrestricted, but we can see that the range is not going below 0. It's approaching 0. So my range is going to be from 0 to infinity, but the difference is here, 0 was defined, right? That's like a point on the graph, 0, 0. But there's no point on the graph that I can do where my y value is going to equal 0. You can see it gets really, really close to 0, but it's not actually ever going to equal 0. So I can't have that as a defined value. So when I'm writing my domain, rather than using the brackets like I used before, I'm going to have to use, again, my parentheses. So let's just go and sketch a quick graph of that. So I have my e to the x, looks something like that. I'm going to say my domain is unrestricted, so that's negative infinity to infinity. And my range, however, now 0 is undefined, right? It's not, I'm sorry, not undefined. It's, it's not undefined, but it's not defined. Well, I guess undefined, right? So that's going to go from 0 to infinity. Okay, last but not least, ln of x, the natural logarithm. And we don't talk about that as much in my class in Precalculus anymore. They took it out of our curriculum, but I still try to bring it up with my students because once they get into calculus, understanding logarithms is very, very important. So we need to discuss it, and I think it's important to expose students to it, even if it's not in my course per se. So here we can look at this. This kind of looks very similar to the exponential graph, which we will talk about. And now you can see that now it looks like the graph is approaching x equals 0, and it's getting really, really close to it. But again, it doesn't look like it crosses it, right? And as I keep on zooming down, you can see that this graph is getting keeps on going down and keeps on getting really, really close to 0, but is actually not ever going to reach 0. And then so it kind of stops at 0, but it continues going on to the right. So the domain is going to be restricted from 0 to infinity, and the range, it looks like the graph is continuing going down to the left. And even though it's like barely, it's slowly increasing, like the rate of the increasing is slowing down, it still is increasing, and I don't see like it's approaching anything. So therefore, we're going to say that the range is going to be continually increasing as well to infinity. So for the ln graph, I'm just going to sketch something like this. And we'll say that the domain is going to be, again, from 0 to infinity. Now, again, I have to use the parenthesis, not the bracket, because 0 is not a defined value. And then my range is going to be from negative infinity to infinity. Okay, so there, guys, is like 8 basic functions that you talk about in like the graph, what they look like, as well as your domain and range. Now what I want to do is kind of take a look at some transformations of the graph and kind of see what's happening and determine the domain and range. So I'm not going to regraph these because I don't really like graphing them from there. But let's just kind of look at like what does x plus 1 do? And one of the main things we're looking at is when we want to identify our transformations, identify if the transformation is happening inside the function or outside the function. And a lot of times we can use that by inside of parentheses and so on and so forth, or the use of parentheses or looking at it, or what actually the function is. And I'll talk about that as we get to it. But you could kind of look at this as that is your function x. And so you could see we're adding a 1 on the outside. So what exactly is that going to be doing to the graph? Well, let's just go and take a look at that. I already have that prepared. So hopefully it shouldn't take too long. So here's x. And if I do x plus 1, you can see that this is actually shifting the graph up 1 unit. Now, as far as the domain and the range, you can see that that's really not going to affect the graph at all. We could also think about this graph being shifted 1 unit to the left, and that just kind of comes into, well, you could also think about this as y equals absolute value of x plus 1. Put the whole thing in parentheses, but I don't want to get kind of too crazy with this. Let's just go with shifting up 1. You could also use shifting left 1. So I'll just write shift up 1. And however, my domain and range is going to be the same. So we'll just say domain from negative infinity to infinity, and my range, that is not a negative symbol, though, so just be careful with that. Don't want to confuse anybody. There we go. And my range is going to be from negative infinity to infinity. Okay, so now let's go and look at y equals negative x squared. And again, going with that idea of, is that negative inside or outside of the function? So here y equals x squared. It looks like the negative is outside the function. Right? I could put parentheses there. And so really what we're doing is we're taking the function x squared and we're multiplying it by negative x squared. So when we do that, let's go and see what happens here. So here's x squared. When I multiply by negative on the outside, you can see what that does. That reflects it about the x-axis. So a reflection, so multiplying by negative on the outside is going to be reflecting the x-axis. Now that happened, a couple things. Now my domain has not remained unchanged. It's still going to graph, the red graph still is expanding left to right. However, my range is completely flipped. Instead of going from 0 to infinity, now it's going from negative infinity to 0. So we're going to say this reflection is a reflect of the x-axis. So to say reflect x-axis. And therefore, my domain is unchanged. So I'll say domain from negative infinity to infinity. but my range now is going to be from negative infinity to 0. And again, 0 is defined, right? So we're going to pull in that. All right, let's go and zoom in the other way. Let's go and look at y equals absolute value of x minus 2. And again, if we look at this, we can see that this is going to be subtracting this outside of the function. You might say, well, when does it get inside? Well, that's coming up next. But you can see we're subtracting this outside of the absolute value. I don't need to put parentheses because we have these absolute value bars there. So let's go and see what happens or how this affects the graph. So there's my v graph, and then when I do a minus 2, you can see that the whole graph is being shifted down 2. So when you subtract a 2 on the outside, that is shifting the graph down 2. Again, my domain was never restricted, so my domain's fine, but you can see that my range was restricted to 0, has now been restricted down to negative 2 because that transformation has helped change that graph. So therefore, this graph is going to be just going to be a shift down 2, so I'll just write shift down 2, and my domain is unchanged, so that's negative infinity to infinity. But my range, though, is again, negative 2 is still defined, so it's going to be negative 2 to infinity. All right, let's go and look at this. Now, the difference here is, see, if I had the plus 2 on the outside, it would look like this, y equals x cubed plus 2. Right? That's on the outside. You can see that I'm adding a 2 on the inside. So what does that do? Because so far we've only looked at operations on the outside. So when we add or subtract a number on the inside, that's not going to affect the graph vertically. That's now going to affect the graph horizontally. And it doesn't shift the graph 2 units to the right, right? Because that's usually what people will think. They think, oh, you know, positive is up, negative is down, so that means positive is to the right, negative is down. And it comes into the basic idea of the transformations function, which is, x minus h. So it's actually the opposite. And we'll get into more details of this, and I'll explain this a little bit further why. But for the case of this, just remember that it's basically a opposite transformation. So when you have plus 2, what's actually that's doing, you can see the green graph, that's shifting the graph 2 units to the left. Now, in this example, my domain and range have no restriction, so it doesn't really affect my domain and range. But as far as identifying the transformation, we're going to want to say shift left 2. So we'll say, oops, my bad. So we'll say, shift left 2. But my domain is still the same. Negative infinity to infinity, and my range, negative infinity to infinity. Okay, so now let's go and look at this. Ooh, so before I multiplied by negative, now I'm multiplying by negative on the inside, and then I'm multiplying by a number on the outside. So we haven't talked about multiplying numbers on the outside. We did multiply by a number on the negative on the inside. So let's kind of see what we got going on here. Let's just, kind of take a look at the graph and see what happens. So I have the absolute value of x, right? Restricted, positive, and for the domain and range. And then what happens here is, oops, I forgot to write in the negative. So let's just do one transformation at a time. That's probably good. So you can see by multiplying by 1/2, what that did is that kind of like vertically compressed the graph, right? It kind of like shrunk it down vertically. It didn't affect it. The domain and range is still the same, right? So it didn't shift the graph up, down, left, or right, but by multiplying by that number, it did affect the shape of the graph. And then if we multiply it by a negative on the inside, you can see that that is going to reflect it about the y-axis. Now, the reflection does change the domain, right? It doesn't affect the range. The range is still from 0 to infinity, but now you can see that the domain has got basically flipped. So there's 2 transformations that's actually going on here. The first one is what we call a vertical compression, because it actually shrunk the graph. So we'll write that in there. We'll say a vertical compression. And I'm just going to write vert because to save my vertical compression, and that is a factor of 1/2. Okay, and then we have a negative, so that is going to be a reflection of the y-axis. So we'll say reflect the y-axis. All right, so we saw that the domain got flipped, so the domain is now going to be from negative infinity to 0, and 0 is still defined, right? It went all the way to 0, and then my range was still the same as the original graph. That didn't change. So that is going to be from 0 to infinity. The graph is just not with that compression. It's just not increasing as fast. So now here is a good one. You can see that here we have y equals, x. And if instead of like scrolling back up, let's kind of look at this. So there's our original function, our parent function. And you can see that I'm subtracting. So if we kind of like put this in parentheses here, we have two transformations. We have the -1 and we have the +2. Now we need to identify when we're looking at our transformations, which transformation is like inside of the function and which one is outside the function. Well, since the -1 is like in the denominator, we could say that that is going to be inside the function. So therefore, that's going to be a horizontal transformation. And remember, it's in the opposite direction. So if it's x minus 1, that means that's going to shift us 1 unit to the right. So I'll just say shift right 1. I'll just say right 1. And then you notice that the 2 is outside, right? It's just like plus a number, like plus k. So therefore, that's going to be shifting the graph up 2 units. Oops, that's a really bad U. So we'll say up 2 units. Okay, so now let's go and take a look at the graph and see, how well I did, kind of based on our understanding. So there's our parent graph, right? And then, look at this. And you see that the graph did get shifted 1 to the right. Like this asymptote here that was at x equals 0 has now gotten shifted over to the right at x equals 1. And then my horizontal asymptote, which was at y equals 0, has now gotten shifted up 2 units to at y equals 2. Right? So you can see here how those transformations work. So by understanding if the transformation is happening inside the function or outside the function can really help you as far as identify the transformations. Now we got to look at the domain. So remember, let's actually go back from here. So remember, the domain of the black graph was restricted on 0. But now since the graph has gotten shifted over to the right, it's true for all values to the left of 1 and all values to the right of 1. It's just not defined for 1. So the domain is going to be all real numbers except when x is equal to 1. And the range used to be undefined for when y equals 0. Now it's defined for all values except for when y equals 2 below, and then for all values above 2, but not when y equals 2. So my domain, again, we're going to use that interval notation, is going to look something like this. So I'm going to write domain. Let's see. So that's going to be from all values to the left of 1. So that's going to be negative infinity to 1. And then from all values to the right of 1. And again, remember, I'm using those parentheses because 1 is not defined. And then we'll just connect those with the union symbol. For the range, again, that's going to be from negative infinity to 2. And then from 2 to infinity. And again, we'll just use the union symbol. You don't have to use the union symbol, but it's just nice to kind of understand that how those are connected. All right, so previously we looked at, well, what happens when we multiply a number in front? We could see that compressed the graph. So what happens if we multiply a number, that's not less than 1, but that's larger? So that is going to affect the graph kind of similar fashion, but a little bit differently. So let's go and take a look here. So now this is kind of interesting. Well, you can see what happened is you can see like the graph, kind of looks like it went shifted up, but technically it really didn't get shifted up, because you can see like the whole graph, like if it got shifted up, that means the asymptote at 0 would have been shifted up 2 units. And the asymptote did not get shifted up 2 units. The only thing that happened was the y-intercept got shifted up 2 units. So actually what happened was the graph got vertically stretched, because you can see that the graph still approaches 0, right? The graph really actually didn't just get shifted up 2. If I wanted to shift the graph up 2, I would add 2. And now you can see how the graph got shifted up 2. So what's happening is the graph is being vertically stretched. So when you multiply by a number outside of the function that's larger than 1, that's actually going to be vertically stretching. When the number is between 0 and 1, meaning it's like a fraction or a decimal, that's going to be a vertical compression. So what's actually happening here is that is a vertical stretch. So we'll just say a vertical stretch. And I'll say that is a factor of 2. Now, let's kind of, again, remember as far as our restrictions, as far as on the domain and range. The domain is unrestricted and the range is restricted at 0, but just by stretching the graph, that doesn't affect the the range either. Like the graph just got stretched. It still was bounded at 0. So my domain in this case is still just going to be negative infinity to infinity. And my range in this case is going to be from 0 to infinity. And again, I'm using parentheses because 0 is undefined. All right, last but not least, ladies and gentlemen, the last one, logarithm. Now, this one is not fun. It's a little bit of a harder question, one that I usually don't get into much with my Algebra 2. Mostly if I'm just teaching an Algebra 2 honors, I'd go over a problem like this. But I just thought it'd be kind of interesting because here we have a number that's inside the function. So when we were multiplying outside the function, that was vertical stretch and compression. So guess what? When you have a number inside the function, that's going to be a horizontal stretch and compression. But I also decided to throw in a horizontal shift because it's something that gets a lot of students and it gets kind of confusing. So it's really important when we're looking at this, and notice everything's inside the function. That's why everything is going to be a horizontal transformation. But it's important when understanding the transformations here that we write this so we have an identified multiplier, like what actually are we multiplying by, as well as what are we shifting left or right. So the best way to like understand this, and we get into this further into the class, so if it gets a little too confusing, don't worry. But if we factor out a 2, x minus 1, now you can see that this is the number 2 that we're multiplying by. And so you can see here, like I have the value of x, right? Like that x has a coefficient 1. That's what we want. And then you can see now this is my transformation. So by looking at it this way, we can see, okay, so my graph is now, I can say it's being shifted by 1. Because if you look at it like this, you might say, oh, it's just being shifted by 2. Now this 2 over here, when it was on the outside, it was a vertical stretch. So might people say, well, maybe then it's going to be a horizontal stretch. So rather than just telling you what it is, let's go and take a look at this and see how this graph gets affected. So here's our normal graph, or our parent graph. And now you can see that the graph is indeed, let's zoom in here. You can see indeed that the graph is only being shifted, over, oh, I forgot I got shifted up 1. There's the same point. You can see that the graph is being shifted over 1, but then there's also, and to make things even more confusing, it actually also has a horizontal compression. And the horizontal compression is very similar to like a horizontal stretch. So it's not actually being, that 2 is not actually being a vertical stretch. It's actually complies a horizontal compression, but it looks very similar. So you can see like the reason why it's being shifted over 1, as you can kind of see, it might not be as apparent here. Here, the asymptote, the vertical asymptote was at x equals 0. Now you can see that this vertical asymptote is at x equals 1. So therefore, and indeed, the graph did get shifted over 1 unit to the right. What's affecting this graph in addition to just that is that I also included a vertical or horizontal compression, and that's affecting the x-intercepts as well. So that's why this doesn't look like it's a perfect shift over 1, because the graph got horizontally compressed. So let's go ahead and take a look then. Now again, so if we look at the horizontal compression is something we're going to want to like write down, obviously, but it doesn't affect the graph. So I'm just going to write. So I'm just going to write the horizontal compression factor of 2. And then we also said that the graph got shifted right 1. So right 1 unit. Okay, now again, how is that going to affect my domain? Well, it doesn't really affect the range at all, but the shifting right 1 does affect the domain, because remember the domain was originally restricted from 0 to all positive numbers. So now my domain is again going to be from 1 to infinity, and my range is still unrestricted, so that's going to be from negative infinity to infinity. So there you go, ladies and gentlemen. That is some basics of transformations to help you in your pre-calculus class. I hope to help. Take care.